So we're going to be looking at projectile motion. A projectile is an object in free fall. So we did a little bit of projectile motion last year, but we kept it in one dimension. We were either launching objects straight up or straight down or dropping them. Now that we've learned vectors, we can handle two-dimensional projectiles. First of all, a little thought puzzle. I'd like you to imagine that a mass is held at shoulder level and fired horizontally. Pretend my Nerf dart gun is held exactly level when I'm standing up, and I fire this dart horizontally. Which of those four paths will the dart trace out? Path A, where it drops straight down. So that's path A. Path B, path C, or path D. You know what? Let's vote. Again, how high you hold your hand up is how sure you are of the answer. So if I were to launch a projectile from a little shoulder-mounted Nerf dart gun, dead horizontal, what path would it trace out? Who said, Mr. Dewick, path A, because gravity's going to pull it down, path A? No one says path A. Okay. Path B. 1, 2, 3. Path C. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Path D. Path D, we jokingly call that, and this might tell you how old I am, we call it Roadrunner physics, because from the old Roadrunner coyote cartoons, the coyote would run off the cliff, come to a stop, and only when he realized he was in free fall would he then start to fall. So path D is nonsense, because there's no way that gravity doesn't start acting on an object right away. You agree with that? Then all of you that picked path C fell for Roadrunner physics. There's no way that gravity doesn't start acting on the bullet or the projectile right away. What do you think? It goes in a straight line for a while, and then suddenly gravity wakes up and says, oh, hello, I wasn't paying attention. I'll start pulling on you now. Objects start to free fall right away. The correct answer here is B. And defend your answer. Gravity acts instantly. It's not your fault because you've been lied to by movies. In movies, you've been taught that bullets travel in a straight line. They don't. All of you have seen this classic scene. It's an action movie and there's a sniper. And they want to build up suspense. So they show you the view through the sniper's scope. You've all seen that? And they have a little crosshairs, and the sniper lines up the crosshairs on the target. If that's all it took to be a sniper, any idiot could be a sniper. You just line up the crosshairs. In real life, they're not aiming at the target because that target is so far away, they know the bullet's going to drop 10 centimeters, 15 centimeters, 30 centimeters. They're aiming way away from the target, above the target, and that's why it takes practice to be a sniper. For really long shots, I'll answer your question in a second, they even have to take into account the curvature of the Earth, because that makes a difference. Earth, sorry people, is not flat. Yes?
Have you seen American Sniper?
I have not. Did they go into it? Yeah, I have. No, I haven't. Okay. Okay. Bullets don't travel in straight lines, but Hollywood has conditioned you to believe that that's the case. As soon as the bullet leaves, it's in free fall and arcing down. It's in free fall. Any projectile is in free fall. The correct answer is B. All right, thought puzzle number 2. Suppose we have two identical objects and they're held at the same height above the ground. Object 1, we're just going to drop. We're going to release it. It's going to fall straight down. Object 2, we're going to launch from that Nerf dart gun again, dead horizontal from the same height as object 1. And Kevin, we're going to launch them simultaneously. Which one hits the ground first? Here are our options, and again, we're going to vote. Option A is object 1 because it has the more direct path. Option B is object 2 since it's moving faster than object 1. Option C is they're both going to hit at the same time. Ooh. If you drop an object and fire an object simultaneously, which one will hit the ground first? Let's vote. Who says, Mr. Duke, obviously A, because it's got a straight path, it's traveling less distance, so A. Was that a vote? Is that a vote? Not sure. No? Okay. Who says, no, B, because it's got speed. It's going to be going faster, it's going to hit the ground sooner. One. Who says C? It turns out you can buy an apparatus that does this. I have one that doesn't work, and so I've never bothered setting it up. But MIT has a pretty good one. What's the video that I want to show, Mr. Duke? Shoot and drop. So here's our apparatus. We have a little spring-loaded cannon. If we arm it, on the left we have a billiard ball with a hole in it. When we pull the trigger, that peg goes out and the billiard ball just drops straight down. On the right, we've got a billiard ball sitting on that platform. It's going to get launched sideways. So let's do the experiment. What's the correct answer, Mud? They both hit at the same time. Why? Yes?
What if like the one that's being projected out?
Like a bullet, you say? Good question. I think I got to pause the video because YouTube's probably going to give me a copyright violation on that one. So the real question is why? Why do they hit the ground at the same time? Well, this is kind of a job for a free body diagram. If I throw something to Mud at the back of the room, the second it leaves my hand, once it leaves my hand and is in the air, what are the forces acting on it? Get the obvious one. And we're going to ignore air resistance. So what else is acting on it? Nothing. There's a vertical force acting on it. Starts with letter G, everybody. Gravity. Can I take the hoodie off just so I know you're not got headphones in? Thanks, kiddo. There's no horizontal force acting on it. By the way, if there's no horizontal force, what's the horizontal acceleration if there is no force as a number exactly? There's no horizontal acceleration. There's a vertical acceleration of negative 9.8. And what we're going to do to analyze projectiles, we're going to set them up in what we're going to call a T-table. One column is going to be horizontal, one column is going to be vertical, and the biggest challenge is going to be, don't you dare put a horizontal value into your vertical section, and don't you dare put a vertical value into your horizontal section. So, explain your answer using relevant physics concepts. Gravity is the only force acting here. This is not immediately intuitive because we're not used to thinking two-dimensionally in components. But anytime you throw a projectile, anytime you launch a projectile, its horizontal speed is constant. Its vertical speed is changing. In fact, I can even be more specific. Its horizontal velocity is constant. Its vertical velocity is changing. What this demonstration shows you is that the horizontal and vertical motions of a projectile are independent. They don't affect each other, Zach. What happens horizontally does not affect what happens vertically. Both masses have the same vertical motion because they're both traveling through the same vertical distance and they're experiencing the same vertical acceleration, so they have to hit the ground at the same time because that's free fall. One will travel further horizontally, yes, but that's completely independent. So the key idea, what's the horizontal acceleration of any projectile? AX equals 0, exclamation point, exclamation point, exclamation point. That you're going to need to, I guess, commit to memory, but you will. Example 3, next page. If we look at a strobe picture of a projectile, we find that it's moving at a constant horizontal speed. Each horizontal, suppose each of these photos is every 1/10 of a second. Zach, you'll notice the distance it travels horizontally is the same every 1/10 of a second. Why? No acceleration, constant velocity. You'll notice the vertical distance changes. Why? There is a vertical acceleration, negative 9.8. I have a pretty good sim here, I think. Just see. Pause for 1 second. So this is a nice website that has some really, really nice simulations. So here's a cannon, and I'm going to fire it horizontally. Can I get it dead horizontal? There it is. All right. I'm going to turn off air resistance. I've got it toggled off. I've got gravity at 9.8. And you know what? I think I need to go to the intro here. This is the one that I want. Air resistance is off. I'm going to turn on the velocity component vectors and watch what happens when I fire this. I'm going to fire it in slow motion so you can see what's going on. What do you notice about the horizontal component of the velocity? Never changed. Why? No acceleration. What did you notice about the vertical component of the velocity? Hey, let's fire it again. It starts out really small. In fact, for a split second, it's 0 because it hasn't started falling yet. And then it's slowly going to get bigger in the negative direction. Why? Gravity. See it? What about acceleration? Just gravity. Unchanging. Always negative 9.8. So, Vx is constant because Ax is 0. Vy changes because Ay is, everybody, negative 9.8. Okay? It says give reasons for your answer. That's why it changes. No horizontal force, therefore no horizontal acceleration. And yes, we're ignoring air resistance. Oh, we're also pretending the Earth is flat, because if you launch a projectile several kilometers, then you would technically have to take into account the curvature of the Earth. We're not getting into that. Here's another nice little toy. This one costs about $400. So we have a golf ball gun on a cart. What we're going to do is we're going to give this cart a big push sideways to the right. Right when it gets to here, this little vertical line, that's going to trigger the golf ball gun to fire the golf ball straight up. If what I've told you is true, if what I've told you that Vx is constant is true, that golf ball should stay right above the cart the entire time. The cart should not get ahead of it. The cart should not get behind it. Let's see. So we arm the cannon. Here we go. Yes? Let's watch that again in slow motion. Now, let's be fun. If you watch really close, you might see Mr. Dewick, it's actually a few centimeters ahead, and I know why. It's really difficult to get the cannon to fire at exactly 90 degrees. I'll bet you it fired at like 91 degrees, and it gave the golf ball a tiny bit of a head start as well. It's really tough to get it to fire exactly straight up, but pretty close. Okay? Pretty close. So, example 4, we have a stop action picture of a projectile being launched from the ground at an angle. Did I say angle? Your line is going to be components. Did I say angle, everybody? We're going to think components here. It says, at each point along the path, indicate the velocity components. Well, if Vx is this big, Danica, it's this big there, it's this big there, it's this big there, and it's this big there, because Vx never changes. So draw that in. What about the vertical component? Well, it's at its maximum right when you launch it from the ground. So that's why it's that big. Right here, will the vertical component be bigger, smaller, or the same size as originally? Vertically, what's happening on the way up? Are we speeding up or slowing down? Yeah, the vertical component here is going to be a little bit less. In fact, Braden, right at the top for a split second, what's the vertical component exactly as a number? So as a number exactly, yeah, I'm not even going to draw it in. In fact, the only component left at the top is Vx for a split second. Then we start to go down, and you know what else? Because projectiles are symmetrical, Braden, when I get to the same height on the way down as on my way up, the vertical component will be the same magnitude but pointing downwards. And right when I hit the ground, the vertical component when I hit the ground will be the same as when I left the ground, but pointing downwards, because what goes up must come. This is if we ignore air resistance, which we are. If I actually wanted to find the velocities, how do I add two vectors together? Draw them. So, don't write this in. I'm going to add it, don't you? That would be the, oh, hang on, change colors, Mr. Dewick. That would be the velocity. Here, Vx would be the velocity, because when I add 0 to Vx, I just get Vx. That would be the velocity, and that would be the velocity. But that slanty one is so tough to deal with, Karen, we're never going to use it. As soon as we can, you give me an angle, I'm going to find its components, and I'm going to deal with that. Example 5 says, indicate velocity components on the stop action picture, and then fill in key facts. Okay, well, the components would go like this. there would be Vx, there would be Vy. Except I'm going to call it Vy initial. Why did I put an initial on the Vy, but not on the Vx? Because there's no acceleration on the Vx. So Vx initial is Vx final, is Vx middle, is Vx anywhere, and I want to reinforce that. The one that's changing is the vertical component. At the top, for a split second, all we have is Vx. Vy at the top is 0. When we get even with the launch again, Vx hasn't changed. Vy would be negative Vy initial. And then just before impact, we have Vx. Vy would be much larger. Not 0, though. You might recall last year, whenever you said that an object would hit the ground at a speed of 0, and in fact, yesterday, I would say, oh yeah, do a belly flop off your cement, off your desk onto the cement. It'll hurt. It's not 0. Vy final will be something. You starting to see how we can break this up into components? We're going to do some with numbers in a second, but key idea then, horizontal speed is constant because Ax is 0. Vertical speed is changing because Ay is negative 9.8. And the horizontal and vertical motions are independent. What does that mean? Don't you dare put a vertical value into a horizontal equation, Zach, and don't you dare put a horizontal value into a vertical equation. The one that you can put into everything is the scalar, time. And what that means, Garrett, is we're going to spend most of our time finding time. I came across this on YouTube. I thought this is a really nice example to show you if you're moving sideways, you are moving at a constant horizontal velocity. See? Vertical acceleration, yes. Horizontal velocity, constant. No horizontal acceleration. I like example 7, I like example 7, I like example 7. Example 7 is a nice question. This I call being launched horizontally from a cliff. And I'm just going to do a spoiler alert. You're going to be asked to deal with 3 projectile situations. Horizontally from a cliff, which is the easiest, even though kids find it tough, it's the easiest. Ground at an angle. Did I say angle? The toughest one is from a cliff at an angle. Did I say angle? Components. Here, it says find the flight time. I'm going to call that part A. And the range, I'm going to call that part B. The range is the horizontal distance from the base of the cliff. How far the projectile travels horizontally. David, can you read to me the hint? It says hint, and then what does it say? T-table. Okay? You might recall last year when we did forces, our go-to was this is a job for a free body diagram. That was our handy dandy little hook. Hey, our handy hook for a projectile, if you give me a projectile, I'm drawing what I call a T-table. What do I mean by a T-table? I'm going to draw it right here. It looks like a letter T. One column is going to be horizontal. I'll use an X. One column is going to be vertical. I'll use a Y. You could also use H for horizontal and V for vertical. I don't care. And I'm sure in some of my answer keys I flip-flop. And then I always write down what I'm going to call my 2 physics no-brainers. They're not no-brainers. You need to know some physics. But now that I've told them to you, you can write this down every time right away without even reading the question. You can say AX is 0 and AY is negative 9.8. How many pieces of information, Sarah, do I have in the horizontal column? Say 1. How many do I have in the vertical column? You might recall from my kinematics equations from D and VI, and I need 3 things to find the 4th. So now I'm going to start to list what the question has told me, putting it into the appropriate columns, and I'm going to, once I have 3 things, find time. Okay? This 20, it's a velocity. How do I know? Horizontal or vertical? Look at the arrow. Okay, Vx is 20. I know 2 things. I need 3. That 50, is that vertical or horizontal? What is it? It's not a distance, it's a displacement, which means, Kai, what's that mean? Are you typing with 1 finger? No. It means dy is going to be not 50, but what? Negative 50. Okay, I pulled everything from the diagram. Sarah, how many things do I have in the left-hand column? What about the right-hand column? Vertical. I can't solve this. Or can I? It really doesn't work with the mask on, does it? Doing the Dr. Evil thing, but okay. I heard you murmur something. What did you say about vertical velocity? Oh, I thought I heard you murmur something. I know one more thing. This is what makes the horizontal from a cliff questions the easiest to solve, but the toughest to have the aha moment. Mason, you need to realize I know Vy initial. Right when it leaves the cliff for a split second, what's its vertical velocity? 0. It's not clear in the picture, but don't you dare tell me Vy initial is 20. That's putting a horizontal into a vertical. I will give you a stink eye like you wouldn't believe. Ding, 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 ding. Sarah, is there a column I know 3 things? I can find time vertically. If I knew 3 things in the horizontal column, I would find time horizontally. Sarah, I'm looking for an equation that has an A, a D, a VI, and a T in it. There is one. Yep. D equals VIT plus a half AT squared. In fact, that's the one you're going to use by far the most. D equals VIT plus a half AT squared. But Sarah, I'm going to modify it just a bit because I don't want to make silly mistakes. So everybody look up, please. That's going to be vertical. That's going to be vertical. I'm going to put Y's under every vector just to reinforce. I better make sure I put a vertical value in. Sarah, I can do one more thing. Ha ha! Why? How come? Okay, and so now I get a special subcase. Now I get dy equals AYT squared over 2. That's still a half AT squared. If you really feel like you got to put the 1 in front of the A, go ahead. But Taryn, I say no. That's much nicer because I can get the T by itself without the quadratic formula, because this on its own is a quadratic equation, and we will have to solve it quadratically for cliff at an angle. Spoiler alert. But this one is not so bad. How would I get the T by itself? Times by 2, divide by A, and then what? Oh, we need to review this. Okay, so it's going to be times by 2, yes? Divide by AY. That gives me T squared. Sarah, how to get rid of a squared? Yes. So it's going to be the square root of 2 times negative 50 divided by negative 9.8. How long is this object in free fall for? 2 times negative 50 divided by negative 9.8, square root, answer button. I get 3.19438, blah, blah, blah. Because I'm going to use this to find something else, trust me, I'm going to write down a few extra sig figs and then I'll round off. I'm going to write 3.19438. And then I'm just going to say, okay, 3.19 seconds. Sarah, how long is this object in free fall for? I'm going to ask you the same question. I'm just going to phrase it differently, but I want the same answer. How long is this object moving sideways for? So are you saying because time is a scalar, I can also put t equals 3.19 in my horizontal column now that I have it? Ooh, Sarah, how many things do I now know in my horizontal column? Then I can find a fourth. Sarah, what does part B want me to find? The range is the horizontal distance, that's dx. I've scrolled down, but you still have it. I think I'm looking for an equation that's got a v, an a t, and a d in it. There is one. It's the same one we just used. It's this. dx equals vit plus a half at squared, except that's ax and that's vx. Oh, which one of these is 0? This time, this whole term vanishes. This is by far what makes kids the most nervous. The number of times I've seen kids put the negative 9.8 in here because it creeps them out to have that whole term vanish. No, 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 no. It makes it much nicer. You want the range? The range is Vx times t. What was Vx, Sarah? 20? And then t, I'm going to write 3.19, but you know I'm using my answer button. How far from the base of the cliff does this object land? 63.9 meters. There is our first projectile question. Use a t-table. Components, ax is 0, ay is negative 9.8. Clearly, I haven't even come close to finishing the lesson, and the tone's going to go in about 3 minutes, and you've all been very patient with me talking. Owen's going to open his eyes. We're going to pause here. If you know that you're going to be really busy next week or on the weekend, you can start some of the homework. If you want to, you're technically, since I've done one example with you, capable of doing number 1 on a separate piece of paper, but I'll give you some time to work tomorrow as well.